Hey everyone, and I'm Beyza, a research scientist at Cohere Labs, and I'm very happy to be hosting today's talk. It's a pleasure to introduce our speaker, Sharon Lee. Sharon is an associate professor in the Department of Computer Science at the University of Wisconsin-Madison, and her research focuses on the foundations of reliable intelligence. How can we build machine learning systems that can recognize unfamiliar situations meaningfully, quantify their uncertainty, and behave reliably when deployed in the real world? More recently, Sharon and her group have been extending this research agenda to reliable agentic systems and inference time reasoning. I have personally followed Sharon's work for some time, and I always find her papers insightful and inspiring to read. And today's talk asks a particularly important question: does an agent know when it is lost? And Sharon will discuss why uncertainty quantification for interactive agent is fundamentally different from uncertainty in single-turn question answering, and how uncertainty and progress can be tracked throughout a long horizon interaction. This topic is highly relevant to many of the questions we are exploring at Cohere Labs around reliable models and uncertainty, quantification, and evaluation. And we are very excited to hear more about this work. And before we begin, just a quick note, we will have time for questions at the end of the talk. So please feel free to keep your questions for the Q&A session in the end. And yeah, Sharon, thank you very much for joining us, and the floor is yours.
Thank you, Beyza, for the very kind introduction, and thank you so much for having me. It's a real pleasure to speak at Cohere Labs. Today, I want to talk about a question that I think is becoming unavoidable for anyone building or deploying LLM agents. How do we make these systems reliable? Not in the benchmark sense, but in the deployment sense. And so the talk is built around two recent works from my group. The first is a foundational paper on uncertainty quantification for LLM agents, which was just presented at ACL early this month. The second one is a paper called Progress Advantage, which also just won the Best Paper Award at an ICML 2026 workshop. And as I'll try to convince you, these two works are really two halves of one story. So let me start with something we all know, but is worth saying out loud. LLMs have loved the chat box. So a few years ago, the failure mode of a language model could be an incorrect text response or some hallucinated response. And you would read it, maybe roll your eyes and rephrase your prompt. And today, these models would write and execute code. They operate software on our behalf. They make purchases. They even assist in scientific discovery, deep research, and customer support. And so this changes the nature of failure fundamentally. When an agent fails, it's no longer just a wrong sentence on a screen. It's a wrong flight canceled. It's an email sent to the wrong person that can't be unsent. It's a database write that can't be rolled back. And so the core focus of this talk is right here at the bottom of the slide, which is reliability is no longer a property we can hope emerges from the model. It must be engineered into the loop. And so now you may say, well, we have benchmarks for agents, we have leaderboards. Isn't that reliability measurement? Well, leaderboards report end-of-task success rates. That's a useful number for comparing models, but it tells you very little at runtime about a specific trajectory while it's unfolding. And deployment really needs this runtime signals about systems' own behavior. And I would argue that there are two fundamental questions a deployed agent should be able to answer about itself. Question one is, does the agent know when it might be wrong? And that's the domain of uncertainty quantification. And question two is each step actually making progress towards the goal? And that's process level evaluation and reward. And so this sounds like different research areas, and historically they have been, but these are two sides of the same goal, which is agent can monitor themselves. And so this is the arc of the rest of the talk. Before I present these two technical works, I want to give you some brief background on how the field currently measures LLM uncertainty, because we'll need this context and vocabulary. So there's essentially four families. First is token probability methods. You would aggregate output token probabilities into things like negative log likelihood or entropy. And the second is consistency-based methods. Basically, you sample several answers and measure how much they agree or disagree. And semantic entropy is one example here in this category. And the third one is verbalized confidence. You literally ask the model, how confident are you, right? And then the model would, spit out the confidence as part of, this token generation process. And the fourth category is conformal prediction. You can construct these calibrated answer sets with formal coverage guarantees. So this is a very rich literature, but notice what nearly all of it assumes is a single turn question answering setup with a static oracle. And this is also what, Beyza alluded to in her introduction earlier on. And so you would prompt the model once, there's no new information arrives afterwards, and there's only, one correct answer sitting somewhere that you can evaluate against. And I want you to hold that assumption in your head for a moment, because we're going to break it pretty soon. The second toolkit I want to also introduce is the reward modeling. And many of you probably already know about this. And so here is the key distinction between outcome versus process. And so an outcome reward model gives you one scalar at the very end of a generation. So it answers, did it succeed? But for very long trajectory, that's extremely coarse credit assignment, right? If a 50-step run fails, which step is to blame? And so process reward models, or PRMs, try to fix this by scoring every intermediate step. So this early work by Lightman et al. From OpenAI showed how powerful this can be for mathematical reasoning. And my lab also invented PQM, which replaces this original loss formulation with a more principled ranking-based loss to improve this process reward estimation. And more recently, people have started building PRMs for agents, typically via this per step multicolor rollouts or task-specific training. And so step level supervision exists, but it's very expensive. You either have to pay human annotation or, a massive compute for rollout. And it's mostly have been confined to mathematical reasoning, where you can verify these steps and resample freely. So here's the crux of the motivation. Agentic inference has four features that violate the assumptions of both toolkits I just described. First, agents are long horizon and multi-turn. These trajectories can span hundreds of steps, and any method built on this repeated sampling, such as consistency-based UQ or best of n per step, they become computationally unaffordable. And second, heterogeneous entities. The context isn't just model output anymore, right? It interleaves the user's input, tool outputs, and environmental feedback. And so when you compute this uncertainty over this trajectory, whose uncertainty is it, right? The model can contribute to it, but this external environment can too. And certainly, this one really matters for the second part of my talk, which is the actions can be irreversible and they're stateful. And so, like I mentioned, a sent email can not be, unsent, and there's no backtracking. And so that means you can't really do these multicolor rollouts from an intermediate state to estimate the step values, which is precisely, how some of these existing PRMs are usually built. And the fourth one is environment is stochastic, right? A user can reply in many valid ways. and an API can time out. And so these environmental transitions, right, have this inherent randomness in a way that single-turn QA never had to deal with. And so the bottom line here is, hopefully I've convinced you that the single-turn QA UQ methods and PRMs designed for these reasoning models, they don't transfer as it is. So this is the plan for today. I'm going to talk about 2 works and they form one story. Part 1 is our AgentUQ paper, which asks this diagnostic question. It formalizes what uncertainty even means over an interactive trajectory, shows why existing signals fall short, and derives what a good signal must satisfy. And then the second part, progress advantage, this would supply exactly such a signal. And so the punchline, which I'll build more carefully, is that this signal can be free, and it's already sitting inside checkpoints you've computed during the standard RL post-training. So now let's dive in. The first work is jointly done with many amazing people, and it's led by my PhD student, Chung Dayo. And it's also, contributed by a wonderful team spanning UW-Madison, CMU, USC, UPenn, and Berkeley. And so this is also the project page, agentuq.github.io, if you want to go deeper. So let's start by, looking at a concrete example. This is a flight booking assistant adapted from the TEL bench. So let's walk this, through this together. The user says, "I like to change my flight reservation, for a Canada trip." And so the agent asks for a user ID, and the user provides it, and the agent makes a function call, right? Get user details, and it retrieves some structured JSON with name, country, and some reservation codes. And then the agent surfaces the information, right? The flight information. The user picks one, and the agent finds the cheapest option to confirm with the user. And the user said, "Okay, go ahead and make this change." And finally, the reservation is changed in the backend database. So there are 2 things to notice. On one hand, this is genuinely wonderful, right? Empowerment brings convenience. The model has access to databases and tools, and it handles these tedious work on our behalf. On the other hand, look at how many places, right, this could silently go wrong. For example, this wrong user ID could be parsed, or maybe this wrong reservation could be selected, or the to response may be misread. So the question at the bottom of the slide is, can you actually count on a system that's potentially ignorant of what it doesn't know? So what makes UQ and agents fundamentally different from vanilla LLM-UQ? I already covered some of these. The first is multi-turn trajectory over long horizon tasks. And this uncertainty can compound over time. And second is the heterogeneous entities across users, tools, and databases. And the environment and context are dynamic, and they shift through these interactions. And I want to also stress why this problem should really deserve more attention, is because agentic workflows are now exploding in popularity, right? These are highly autonomous systems that are already woven into some of the enterprise or people's workflows. And so we argue that this AgentUQ framework is needed for 2 reasons. First is to sidestep these potential risks, because agents are acting in the real world, right? They can create real consequences, not just incorrect text. And the second is to leverage this rich opportunities, because a precise awareness of the system's knowledge boundary is exactly what unlocks deployment in many, many domains. So if the agent can flag, "I'm not sure here," then you can route to a human, and suddenly, a lot of domain applications in finance, legal, healthcare, right? They become more tractable. So how do we formalize this? The definition one specifies a stochastic agent systems. So we cast the agent trajectory as a stochastic process over 3 variable types expressed as a Bayesian network. And so here this notation A denote the actions, right? That's what the agent generates, either being a message to the user or a tool calling. And the notation O stands for observations. That's what comes back either from the user replies or the tool calling output. And the E stands for environment state. And so that's the latent state of the world, right? Which agent's actions may irreversibly modify. So at the beginning, let's say the environment state is E sub 0. And then the user asks, initiate this query. I like to cancel some of my upcoming flights. And so that's denoted as O0, right? That's the initial observation from the user. And then from there, it would then trigger a new action and also corresponding observation, right, from this environment or the user. And then the environment state also transits from E0 to E1. And so then this kind of, the process continues, right, for many rounds until finally it terminates. Right? So this is the mathematical formulation of this. And further, we under the stochastic agent systems, we have the following probabilistic process, right? At each step, the agent would essentially take an action. And so this A sub I would be conditioned on the environment state and the previous observations. And then a new observation is generated, right, based on the action and the environment state. So this is just to formalize the flow I just described visually in the previous slide. And on the right hand of this slide, you can see that the trajectory has this joint probability that decomposes very naturally into the per step terms. And so this is what I want to kind of dive a bit more into. With this joint distribution in hand, now the definition 2 defines agent uncertainty through this information theoretic measures on it. And now you can see that the total uncertainty, which is this U of F here, so F, that's the entire trajectory, that can be decomposed into the summation of initial query uncertainty, which is highlighted in the yellow box, and the turn level uncertainty in blue. And then furthermore, for each turn, the uncertainty can be decomposed into the action uncertainty, which is how unsure was the action, the agent at each decision, and the observation uncertainty, which is how unpredictable were those external responses. So what's nice about this formulation is that it provides a unified view, and it subsumes the existing UQ literature as special cases now. Or for example, a single-step LLM-UQ problem, which is what most papers study, this falls out as a special case when t equals to 1 and there are no observations or environment involved, right? There's also no users involved here. And reasoning UQ is where there are multiple internal steps. So t is now greater than 1, right? But there's no external feedback or this external environment. So that's another special case. And then the AgentUQ kind of, sits at the very top level that encapsulate all these. So now let me talk about the challenges. Obviously, this is a very, very non-trivial problem to solve, despite its generality. So challenge 1 is about selection of uncertainty estimator. Probability-based methods are theoretically strong and free at inference, but frontier agents typically don't expose those token probabilities. So accessibility is bad. And consistency-based methods are accessible and well-grounded, but resampling a 100-step trajectory several times, this is very expensive. And verbalized confidence is accessible but its theoretical grounding is quite weak. And so this trilemma already exists in the standard LLM-UQ problem, but it's amplified in the agentic setting. And the second challenge is that modeling uncertainty dynamics in these interactive systems. So we actually did this initial experiment by looking at how uncertainty evolves over the course of a trajectory for successful versus failed interactions. And so this is based on the TEL bench. There's the retail and the telecom on the right-hand side. And so what we found is that simple averaging-based aggregation of these per turn uncertainty. So basically you extract this turn level, negative likelihood score, and then you average them, right, into this trajectory level score. And then use that to, as a prediction for the task success or failure. And you see that, these can't really differentiate between the failure trajectory from the successful trajectories. And so these two curves are highly overlapping. That means we need something more sophisticated. And last but not least, we don't have many benchmarks that provide turn level annotation or evaluation protocol. This is understandable because the cost of reliable labeling in these fine-grained units. And so that's another obvious bottleneck that hinders the progress of AgentUQ research. And so beyond these challenges, the position paper also lays out some open questions. And I'll just flag them very briefly here. The first one is intrinsic solution multiplicity. So when per step uncertainty is high, is that because the agent doesn't know what to do, or because there are multiple valid actions, right? So distinguishing these genuine ignorance from legitimate optionality is a fundamental unsolved problem. And second is evaluation beyond task failure. Right now, we mostly evaluate UQ by whether it predicts this eventual success or failure. But can we credit this richer, more nuanced uncertainty signal to capture this subtle behaviors of agents? And thirdly is multi-agent uncertainty. As we move towards systems where multiple agents interact, how do we model their joint uncertainty and dynamics, right? How do we prevent phenomena like debate clubs where agents converge on some confident but wrong answers? And finally, there's a lot of hype around self-improving agents. So when agents' parameters, memory, and available tools evolve across episodes, how should these uncertainty estimate even adapt, right? All of these are vastly open questions. So now let me compress all of part one into this specification. So if you want one signal for agent reliability, part one says, okay, it must be, has this per step, right? Fine-grained credit along the trajectory, not one score at the end. And ideally should be annotation free and with no or minimum human feedback or labels. There should also be no multicolor rollouts because of the irreversible environment. And the third one is stochastic awareness. It should be valid when users or tools and environment inject some randomness. And lastly, it should be cheap and accessible. Ideally, it shouldn't involve these enfold repeated sampling. So that's a very demanding list, right? Every method we have surveyed failed at least one requirement. And so that sets up, the question for part two. Is there a signal, right, that exists as a byproduct that can be maybe sitting in your RL post-training pipeline? All right, so now this will be a good segue to, dive into the second work, which is also led by my amazing PhD student, Chang Dai-Oh, and he really, poured in a lot of effort into this work, along with my other PhD students, Wendy Lee, Sung-Hyun Park, Samuel Ye, and my collaborator Tanwei Malik from Oregon National Lab. And so we're honored this paper recently received the Best Paper Award at the SML RLXF workshop. So let me restate the tension as a paradox. What would per step rewards unlock for agents, right? The first one is, you can do test time scaling by sampling, maybe n candidates and keep the best. And you can also do runtime monitoring, and that's very useful because you can flag a failing run before its actions, actually land, right? Which for irreversible actions, that's the only time it would matter. You can also do failure diagnosis to localize, in this very long horizon trajectory where exactly went wrong, right? So why we can't build agentic PRMs the standard way? Well, obviously because long horizon makes the annotation and rollout exploding cost, and also the irreversible issues we talk about. And so, these agents that really needs the process level evaluations are precisely the ones for which building PRMs is least feasible. And so now to set up this work, I'll first introduce some notations, very simple ones. So we model the agent trajectory as a token level stochastic MDP. And so the state is all the tokens so far, right? It includes prompts, actions, and observations. And the action is, like generating the next token from the policy. And the transition is, in this case, stochastic because, user replies or to output have randomness. And lastly, there's this per token reward. And here's the key observation about how the policy came to be, right? Essentially, all of these modern RL post-training, including RLHF, RLVR, this PPO style, DPO style, they share this one abstraction, which is KL regularized reward maximization. So they're trying to maximize some expected reward while stay within this KL ball of a reference policy. And so the reference could be the base or the SFT checkpoint. So that's the, the abstraction of many objectives here. And so there's this beautiful known results for the deterministic case, right? So in a deterministic MDP, like in plain text completion, that's where, the next state is simply, concatenating the current context with what you have generated, in this current step. And so it's deterministic because that state transition is essentially a concatenation action, right? And so in this deterministic MDP setting, the KL regularized fixed point actually gives you a very clean implicit reward. The reward of a step is recoverable from this beta times the log probability ratio between this trained policy pi star and the reference policy pi ref. And so in this formulation, the value terms cancels out and telescope away along the trajectory. And so it's a very elegant free lunch and has been exploited for implicit PRMs in mathematical reasoning. But, as we move into this stochastic MDP setting, which is for agents, right? This is where, a to response or user reply would cause this transition, randomness. And so that's where this cancellation of the value terms no longer applies. And so you see this residual terms would remain in this equation here, right? They don't really cancel out. And the optimal function, value function V star is not accessible from the policy pair. And so in other words, this log probability ratio no longer recovers the reward in this stochastic interactive setting. And so here's the key idea of this work. It's conceptually very simple once you see it, which is to target the advantage, not the reward, right? So you may be wondering, well, why is advantage even the right thing to want? Because the advantage is the value of an action relative to the policy's average action in that state, right? That's exactly the quantity that drives policy improvement in the first place. So for ranking candidate actions or for judging whether a step helped, this relative merit is what you actually care about. And so now this result in proposition 1 in our paper state informally here under this KL regularized RL in this general stochastic MDP, the optimal advantage is exactly the log probability ratio between the trained policy and its reference, right? So now let's unpack this a little bit more. So here is essentially the statement. If you want to, summarize in one sentence, RL post-training already paid for your PRM. So we're going to have this PI-REF to begin with, right, in practice. And once this PI-REF has gone through this RL post-training, we will have this PI-STAR, which is this our trained policy. And now you can take both of them. The reference and this PI-STAR, and for any step in any trajectory, you can compute this log probability ratio between these two. And that number is what we call the progress advantage. It's a principal per step score, which read directly off, artifact of standard post-training. And so it's nice because there's no annotations involved. There's no explicit reward model training. You just need 2 checkpoints that you already have, right, in this post-training process. So let's now make it more concrete, right, by looking at an actual example of how progress advantage, can, tell us something meaningful. So the user asks us here, can you tell me the latest news headlines for the US? And we're going to generate 3 candidates for the first step. So the candidate 1 calls get news headline with the country US, which seems pretty reasonable. And the second function call, slightly is off because it's calling another country, France. And the third function call, it's actually, called a different function, which is get weather forecast with a, even further drifted away location. So now under these 3 initial steps, we're going to continue to have these, we're going to measure the progress advantage. So in this case, the first one has the highest one. And then the middle one and the right one has negative score in this case. And then from each of those function call, you can have some observation, right? And then finally, the system will generate some response. Here are the latest headlines. And so if you look at how good the final reward is, you will see that in the first case, obviously, it will have the highest final outcome. And so that means the progress advantage that is estimated in this partial trajectory, in this case, the first step, is at least meaningful, right, in predicting this final correctness. So that's one concrete example here. And I also want to mention that you do need some recipes when you go from some theorem to the practice. And so in our work, the first recipe is pick this policy pair. So PI-STAR is any RL trained checkpoint. So here, I also want to highlight another result in the paper, which is proposition 2. That simply states for these post-training objectives that doesn't have this explicitly KL regularization. For example, those clipping-based surrogates like DAPO or GRPO, which enforces more implicit KL constraint. They're actually also covered by the theory, right? So that relaxes the objectives you can apply this progress advantage to. So essentially all those popular objectives in post-training makes our, this progress advantage compatible. And the reference, PyRef, it could be a base model or SFT checkpoint or some previous online round checkpoint. So that's the first recipe. And the second recipe is also important, is how you aggregate these token level ratios, right? Remember, you have this, for each token, you would have this ratio of, log probability between the pi star and pi ref. And then we need to aggregate this somehow from the token level to the step level, and then from step level to the trajectory level, right? You could aggregate this through summation or averaging or taking the minimum or the maximum, right? There are various ways to do the aggregation. And it turns out that the best combination can be task and model dependent. And I'll talk more about this point in one of my experimental slides, just to back this up. All right, so how does progress advantage work empirically? So my student really did a lot of hard work experimenting across 3 applications. So the first one I want to share with you is test time scaling. So what we did is to sample 8 trajectories and then use progress advantage to pick the best one. And then we're going to measure the success rate. This is averaged over 4 benchmarks here specified at the bottom of the slide. And in the actual paper, there's the detailed breakdown of performance for each of them. So first, let's look at the Gamma 4B model. So you can see that the greedy decoding, which is the leftmost bar, gets only 33.4%. And then the best trained reward model, which the second group in this figure here, it barely moves the performance. Now it's 33.6. And the best confidence method actually hurts in this case, which is 31.4. And progress advantage, which is the fourth group in this figure here, improves this to 38.8. So that's a much more meaningful jump, which is 5.2% improvement. And we also show this, the AUROC performance, which is when you have the ground truth best trajectory, right? And that gives 45.4%. And then we can also look at the same trend on another model, which is Queen 3.59B model. Again, the baselines land somewhere around 55%, and progress advantage improves this to 62%. And that's, very significant improvement over the best baseline. And moreover, it gets meaningfully close to the AUROC, which is 67.5. And so the takeaway here is, this zero training signal without any explicit reward modeling can actually beat this trained reward model at their own game. So the second application I want to share is the uncertainty quantification, which in simple words is, will this trajectory succeed? And so we measure the AUROC, which is the binary prediction task, right? Whether this trajectory succeed or fail on this TAL airline benchmark. So this result is shown here in this figure. You can see that, let's start from the bottom, right? The trained PRMs actually struggle. So we have 2 here. One is the wild reward 8B model. That's actually below chance correctness. And then the think PRM 14B model does better, but it's still, close to coin flipping. And so this happens because, these trained reward model, they're really good at the task it was trained on, but they can, they can have this transfer failure when there is some, domain mismatch. And so that's expected. And then we also evaluate on this Claude model, which is the Sonnet 4.6 judge. It does better. It reaches 0.64 AUROC. But overall, our method does the best and outperforms these strong confidence baselines like self-certainty and deep conf. And so this improvement is pretty significant, right? It's outperforming both trained PRMs and the frontier model judge. And the third application I want to show you is the failure attribution. So here on, this task is essentially to say, okay, if we have a multi-agent trace that spans maybe hundreds of steps, can we actually pinpoint the step that actually caused the error, which is the decisive error step? And so we took this benchmark called Who and When, which already comes, provides the failure trajectories and the annotation of the step that caused the error. And then we use, progress advantage to see if we can, localize some of those. And this task turns out to be highly, highly non-trivial. And you will see that these pre-trained PRMs and confidence scores, they can barely localize the errors, right, in this long multi-agent traces. And so that's in the blue bars and the pink bars. And the y-axis is the accuracy, right? So those are roughly, all below 10%. So that suggests how challenging this task is. And progress advantage, relatively speaking, it's more promising. And it's those two purple bars, roughly, around 20%, not quite there yet. Again, because this is a very, very challenging task. The encouraging news, though, is that it actually rivals the agent tracer, and that's the strongest method in literature, which is the dashed line. So that's kind of the SOTA performance, which was trained specifically for this task. So those are some empirical evaluations. We also perform ablations to understand some of these design choices, such as the aggregation strategies. And the key takeaway here is that this varies actually, depending on the task you want. For example, for best of n sampling, what we found is the winner is to first take the mean over the tokens, and then take the minimum over the steps. And intuitively, this is optimal because you want to penalize any single weak step. So that's min over the steps is the best, because one bad action can really sink a whole trajectory. And if you want to check, more results, they're all in the paper. I'm gonna, keep this part short because I think we're already out of the 40 minutes allocation. So I'll try to wrap up here now. The takeaway in part 2 is first, there's already free lunch, sits in your RL post-training checkpoints, and the log probability ratio between the trained policy and the reference recovers this optimal advantage. And the second takeaway is that it works with zero training and outperforms confidence baselines and trained reward models across 3 applications, 5 benchmarks, and 4 model families. And the third one is you do need some, practical recipe to make it work, including, picking the checkpoint and the aggregation strategy. But it's nice because you don't need to do this human annotation or explicit reward model training. So now if we zoom back out to this, the overall story I was trying to convey at the beginning of the talk. So part 1 is the framework, right? What uncertainty means over interactive trajectories, why existing estimators fall short, and the requirement a good signal should satisfy. And part 2 provides one instance of that signal, right? That's, ideally should be annotation free, domain agnostic. And of course, there's tons of other possible alternatives you could still explore. And that's still, a very vast open problem space. So what we're really seeking here for is the dynamic reliability for agents in the wild that knows when we're uncertain and measure whether we're making progress towards the goal. And there are many exciting directions where, the work could be taken forward. I highlighted some of these here in the slide. One thing we have been exploring is how do we, extend from this pure inference time work, which I talk about in this talk, primarily to this incorporate these fine-grained credit assignment in the RL post-training process itself, right? So unfortunately, I don't have the time to cover some of these training-based techniques, but I do want to, highlight this another pretty interesting work from my PhD student, Etienne, and also this is in collaboration with folks from Microsoft Research, is turn-level reward assignment via this credit estimations for long horizon agents. And so the key contribution is to provide this or incorporate some of these fine-grained turn level signal into our post training. So you can, check it out offline if you're interested. And finally, I want to give, this enormous credit to all of my students here and the key contributors to these works, Chang Dai-O, Sung-Hyun Park, Tu-En Kim, Jia-Tong Li, Wendy Li, Samuel Ye, Sean Du, Tanwi Malik. And thank you very much. I'm happy to take questions.
Yeah, so thank you so much, Sharon, for this super insightful talk. And yeah, if anyone has questions, please raise your hand and ask your question. But I can maybe start when people are thinking about their questions. Yeah. So in single turn setting, confidence is usually calibrated against whether the final answer is correct. And like for a multi-turn agent, the target is less obvious. So what should confidence at each step actually represent in that case?
Yeah, that's a really good question. I think, even in this single turn QA setting, right? Ideally, what a good confidence should spit out is a calibrated one, like you mentioned, right? It should, align with this underlying accuracy of, the final answer correctness. But I do want to point out that, this existing confidence produced by the LLMs, trained in standard way is not necessarily calibrated, right? As it is. So there's still, challenge in this single turn QA setting of, okay, how do you design the post-training objective, for example, to produce this calibration native confidence scores without compromising too much of the capability, right? There's always the trade-off between capability and reliability that we're talking about. So that's still, I think, an interesting research question on its own. And to extend that into the multi-turn agent setting, I think that definition becomes even more vague now, right? Because, for each turn, there's no ground truth of what that actually stands for, right? You can't easily measure that against, the final answer per se. But what you could, try to think about these intermediate score as, if you think of this as the following way, right? So a score should ideally reflect the probability of reaching the correct final state. And so that actually is quite analogous to this notion of Q value in RL, right? A good action or, a good scoring in that step should, gives us a high probability. If you start, on average, right? If you take, all the possible steps from there, on average, how well you can reach the final goal. So I think that's maybe the way to think about this confidence and score in this multi-turn setting.
Yeah, so you can use this progress advantage score.
Yes, right. So that's the key message here we're trying to convey in this work. Yep.
All right, thank you. Other questions? Yeah, Connor, please go ahead.
Sharon, thank you very much. Yeah, super interesting talk.
Thank you.
I work on Beyza's team, and our team has been working on, yeah, very related kind of concepts around confidence estimation and so on. So this was super interesting.
Wonderful.
When you touch on kind of what the underlying sort of signal you should kind of supervise confidence against, kind of being an open question in multi-turn situations, we were even working on like just a single turn scenario, and our work kind of focused on like separating confidence into two sort of moments of elicitation, even in the single turn scenario, because initial confidence maybe means like how likely am I to solve this question, whereas final confidence means how correct is this specific answer. So that was really interesting. My question is more about the uncertainty quantification application of your kind of the second part of your talk on your approach around the kind of KL between the reference policy and the trained policy. Your calibration results were in terms of AUROC, kind of measuring how well the signal can discriminate between correct and incorrect answers. Assuming you can choose some sort of optimal threshold that'll distinguish between them. But I'd be interested if you did any work on kind of translating that into a probability between kind of like projecting these values to, I guess, the range of 0 and 1, and whether you had any success in kind of absolute calibration in those terms, whether the signal could predict after some sort of projection.
Yeah, thank you, Connor. By the way, I think, the work you described that your team is doing sounds super, super interesting, and I'd be happy to chat more after this talk as well. Yeah, for the application, I think that's actually something we haven't done, but I think that calibration is a very natural angle that's worth diving deeper into, right? As you pointed out right now, so let's go back to this slide here. So the existing evaluation is primarily based on this, matching basically the trajectory level correctness or not. And that's not even, doing calibration per se, right? And so that's actually a missing piece that we didn't do in this work, but I think would be interesting to kind of expand upon in the deeper investigation.
Yeah, that makes sense. Thank you. Because I can even imagine, I guess, this is useful for sort of credit assignment over multi-turn trajectories, but it might be, yeah, interesting to see how like credit assignment might interact with supervision targets for confidence estimation. Like in our work, the initial confidence estimate was a sort of group-wise target. So like over many groups during RL post-training, if you have a group of rollouts, how many of them were correct? And that was our supervision target for a kind of pre-confidence verbalized confidence. And then the post-confidence was supervised against the kind of correctness of that instance, the kind of the specific like whether that specific answer was correct or not. But then it's unclear when you expand it over a multi-turn trajectory, because each individual term might not have a candidate answer, but even if it does have a candidate answer, it's not clear how to distribute all these rewards across the trajectory. I can imagine a scenario where you might use something like this to kind of assign credit along the trajectory, where if the ultimate answer was correct, maybe the supervision target for confidence should be 1, but maybe for intermediate turns that were less important for the ultimate answer, as measured by this sort of signal, maybe you kind of give a different confidence target for those intermediate turns based on the kind of combination of these signals. So, yeah,
right. I think that would be super, super interesting, actually.
Yeah. Thank you, anyway, Sharon. We'd love to talk more.
Absolutely, absolutely. Happy to follow up. And I do want to also, maybe I already mentioned at the end of the talk, there is this new work called Trace that also has a different methodology for estimating this turn level credit. I think it would be interesting to also kind of contrast these methods by connecting to this calibration aspect of it.
Yeah, I definitely agree. And I see a question in the chat by Wilfried. How well does the progress advantage signal generalize to long-running multi-agent workflows where intermediate progress may be non-monotonic and different agents have incomplete views of the overall task?
Sorry, do you mind stating the last piece of the question?
Yeah, of course.
Or let's see.
Like where intermediate progress may be non-monotonic and different agents have incomplete views of the overall task. So the last question in the chat.
Oh, I see. So how well does this generalize to long-running workflows where intermediate progress may be non-monotonic and different agents have incomplete views of the overall task? I see. That's very interesting. I think for the current evaluation, you see a lot of this are based upon kind of more simplified as, like airline tail bench like setup, right? You have this more like this, it's closer to the single agent setting that does this function calling and then return this result. Like I said, I think this multi-agent is still the space we haven't explored it rigorously yet. So I want to kind of be just withhold making speculative comments in that sense, because multi-agent does bring, these additional dimension of, challenges on, this agent interaction and the dynamics among them. So it's still unclear, how this progress advantage would generalize to those settings. But I think, again, those are interesting future work that's worth exploring. And the work is just released last month, and I feel like you guys are already kind of raising several ideas that it can be potentially expanded into. So that makes me happy.
Yeah, sure.
Hi, Sharon. Thanks so much for your talk. It was really great. And it's also very related to our work that we're doing too. I'm also part of Beyza's team.
Oh, nice. Hi, thank you.
Yeah. My internet's kind of bad, so no video work today. But I was curious, is there anything, like, is there a requirement of how well post-trained your RL model is for progress advantage to work? Like, is there some sort of like, I don't know what metric you'd use, but is there some sort of like internal metric you guys use for when the model is ready for progress advantage or giving you progress advantage? Because like, say I take like only 10 steps of RL, at that point, is that model useful for progress advantage? My assumption is it's not, but do you guys have any intuitions on that?
Yeah, this is a great question. Well, what kind of policy or training objective is compatible with progress advantage, right? As I mentioned, this really applies to any of the objectives that's trained with explicit KL regularization, right? But we also prove in proposition 2 in the paper, right? It can be extended and relaxed to this implicit clipping-based surrogates, right? Like DOPL, which is also widely used today. So those kind of mainstream objectives used for post-training is already compatible with progress advantage. But in practice, you do have to make this conscious decision about, okay, which checkpoint to take, because the theory tells you, okay, if you take this optimal policy, then this progress advantage recovers that exactly. But in practice, you don't have access to that optimal policy. So the empirical one you're taking is just an approximation of it. And so we did this ablation in the paper. Unfortunately, I couldn't share in the talk today because I have to cut off a bunch of materials. Is this, how do you pick this checkpoint and how much gap there should be, right? And the sweet spot, what we found is, ideally it should not be too far off, but also not too close, right? If you just train it from the best base model for 10 step, that's not going to work. And so the sweet spot is actually somewhere in between, and we have a figure in this paper that shows exactly this trade-off.
Got it. Okay. Thanks a lot. Appreciate it.
All right, so we are right on time, and thank you, Sharon, for the talk and for answering all our questions. And it was a real pleasure to host you. And thank you, everyone who joined us and contributed to the discussion today. And yeah,
awesome.
Hope to see you in the next sessions, everyone.
Thank you, everyone, for coming and for having me.